Welcome, Marin High School math teachers. This is a video. It's going to take somewhere under 20 minutes, but I want to explain the first project that we have of the year. It's a Sierpinski Tetrahedron project for Marin High School for the beginning of the year. And this picture that you're looking at right now is a Sierpinski Tetrahedron that was built at a university in Norway. And if you look at this is the completed structure, and we're going to be completing this structure, which will be about the same size. It'll be a little bit shorter than this one, not much, but just a little bit shorter than what you see here. And if you look at the face of this tetrahedron, there's a very particular pattern to the face of this structure, and that structure is called a Sierpinski triangle. And there's two different ways I'm going to explain a little bit, so maybe you know, but just want to explain a little bit about Sierpinski triangles first. There's two different ways we can look at it. One is a growth model, where we start off with an equilateral triangle. We take this equilateral triangle and we copy it, and then we put one on each of the base vertices. So now we have this second order triangle. Now we're going to take this entire structure and copy it and put a copy at each of the base angles of that equilateral triangle. And then we have this third order. Now we're going to take a copy of this whole structure and put a copy at each of the base angles there. Now we have a fourth order. And you could keep going on and on and on forever, but this is a growth model. You started with a small triangle and it kept getting larger and larger and larger. You can talk about many things and tie this into any one of your subjects, Algebra 1, Algebra 2, Geometry, pre-calculus, even calculus. There's a lot of different ways you could bring in summations, you can bring in different kinds of number patterns, you can talk about things getting larger and larger, infinitely large, growth models. There's exponential patterns here. There's a lot of different things going on, and so you know, look it up online and find those connections so that you can talk about this in class as we move forward. Again, it's called a Sierpinski triangle, and the other thing that's really fascinating about this is historically we think a lot of the math that we study and the students study is math that has been discovered, and some of it thousands of years ago, and they don't necessarily realize that there's still many new and exciting things that happen in mathematics. This Sierpinski triangles is a type of fractal. And fractals are relatively young. When Sierpinski first came up with this structure, it was in the early 1900s, like 1910, 15, I can't remember the exact year, but and it really didn't become the big discourse in mathematics really didn't start until the 1970s with Mandelbrot, and also the advent of computers, which could create fractals much faster and more eloquently when you could make a computer generated. And some of you can, you know, I've got fractals on the wall in my classroom. They're just absolutely beautiful. But so this is just one of the simplest fractals to examine and to look at. It's also, fractals is another name for it, is looking at self-similar objects. A great video that's a fun introduction for the students is something by Vi Hart, who in one of her doodle blogs on binary trees, she talks irreverently about what it's like to be a math student and what teachers ask. I think they're great. The kids really enjoy them because they relate to what she's saying. But she does a lot of doodling that becomes Sierpinski triangles, which is kind of fun. So I showed you the growth model aspect, but this next one is where instead of where the structure itself keeps getting larger and larger, we're going to have a constraint on the outside edges of the structure, and the Sierpinski triangle is just created by finding midpoints and connecting midpoints over and over again of particular triangles. So here is I'm going to kind of speed it up. This is the Sierpinski triangle where you start from an outside equilateral triangle and then just keep dividing them smaller and smaller. And so here you can be talking about how infinitely small things. So how small is small? Can we keep going? How many iterations can we do? Can we keep doing this forever? There's a lot of things you could bring in here. It also, for summation in Algebra 2, there's numbers that can be associated with this. You can talk about size and geometry. There's a lot of the area of the triangles, what's happening to the areas as they get smaller and smaller. What's the ratio of this large triangle here to, say, one of these little triangles. it'd be interesting that throughout the year you could relate a lot of the different topics back to these structures, and it's kind of a cohesive thing that all of our subjects and all of us in all of our classes could have this common theme. I think it's a neat way to tie in all of us together throughout the year. So I believe that's six. 1, 2, 3, 4, 5. Yeah, the 6 orders in that Sierpinski triangle there. If you colored these in different ways, kind of like, quilting, you'd get really interesting patterns besides just the triangles that you see here. It's kind of fun to do that. Here's something else to tie it in that I think is fascinating. That if you know Pascal's triangle, which of course Blaise Pascal got his name because he had great PR, but it was discovered hundreds of years before Blaise Pascal in China. But here's Pascal's triangle. If we superimpose Sierpinski's triangle over it, there's some really interesting things, and this would be kind of a fun one to do with the kids for an activity, just to have them come up with Pascal's triangle and draw a Sierpinski triangle over it and see what they can come up with. So, okay, what do you notice? And just leave it at that. And some of the things that they might come up with is, well, there happen to be these empty triangles. And no matter how big you make Pascal's triangle and then have a Sierpinski triangle laid over it, you will always have these. So I'm going to color those in black, and you might notice a few things, and some of the things, oh, they all point down, and there's a lot of different things. They're all what I call the 1-unit triangles. They're not 1 unit, but it's the first order, okay? So the first order triangles, but all of the downward pointing first order triangles are the empty ones. All of the upward pointing ones have a number in them. Well, I'm going to color in all the upward first order triangles blue. And I'm going to color in all the other triangles red. And that's another thing. You say, okay, what do you notice here? Well, this to me, like, why is this happening? All of these blue triangles are odd numbers, all of them. And all of the numbers in the red triangles are even. Why is that? Let them think about it. Let them study. Don't answer these questions for them. Just have them think about it. Have them study. This is one of the things that mathematicians love to do. So it's an interesting thing to look at these kind of patterns and ponder about them. They might come up. The possibility that they could come up with something nobody else has ever thought of is possible. It's out there. We take it to the third dimension, and we get the Sierpinski tetrahedron. This is actually Alexander Graham Bell and his wife kissing in a Sierpinski tetrahedron. I think it's kind of cute. This is a structure called Bat Country that was created by Gwen Fisher and Paul Brown, who are the creators of Doceri. Paul Brown is the creator, and they work together on it. So they created this program that I am using to make this video with, and they made it for Burning Man, that I believe is in Nevada, and they did it several years back. But these are made out of aluminum bats and baseballs, and then they're bolted all together, and it makes an extremely strong structure when they were done. I think they've had somewhere up in like 30 people, 35 people on this structure at the Burning Man venue. Then also there's lots of things online. Here's something out of the Make Online magazine. This article here, which is on Sierpinski tetrahedron, was written by George Hart, who happens to be Weihart's father, who was a very renowned mathematician in his own right. Has done lots and is very involved in the Mo Math Museum back in New York, and you should look that up online. It's got a lot of fascinating things as well. So we're going to work in there. So what is it that we're going to do? Well, we're going to be creating a whole bunch of first-order tetrahedrons. We're going to take 4 of those, and every group of 4, we're going to make a second-order tetrahedron. And then we're going to take every 4 of the second order and make a third order. And so we'll have a bunch of those. And at the end, we're only going to have 5. In the very end, we're only going to have 5 of these. We're going to have a whole lot of these, and we'll have fewer of these. Only 5 of these when we're done, and then we'll take those 4 of them and create the fourth order tetrahedron. This is going to be a fascinating structure. I want the kids to figure it out, but for your information, this height right here is 9 feet. A little over 9 feet. This whole structure is like 19.6 feet tall. That's 2 stories. So this is going to be a huge structure that we'll be able to create out in the quad. We'll be doing all of the first order in the classroom, the second order in the classroom. We will probably have to build these third orders in the student center because they're 9 feet tall and they're also 9 feet wide. So I don't believe we can get them out the classroom doors. So we'll probably have to make these in the student center. And then on Monday, the second week of school, we will, at lunchtime, gather together, get our students to come out and help us, and we will create this fourth order structure. There's probably going to be people clicking pictures, and we might have people from the district and perhaps even some people from the media coming and taking pictures of what we're doing, because it's going to be pretty showy when this goes up. This is not as easy to construct when we put it all together, and I'll describe why in a little bit. The big question is, how do we do this? You need to know how to do this very well before we start asking the students to do it. So, how do we do it? First of all, we will gather together the supplies. The supplies will consist of cord, some type of a dowel or a pencil, something that will keep the cord from slipping all the way through the tubes, because you're going to feed the cord through the tubes and then pull, and so you need something to hold it at the end so it won't just pull out. You can't just tie a knot. These are 1.5 inches in diameter, so that it would just slip right through. So we need something that will keep that from happening, because you're going to cut a piece of rope. You're not going to have the whole big spool of rope there. Now, you need 6 dowels total, but what you're going to start with is 3 dowels. And this video is going to show how the cord goes through those dowels. How the cord goes through the tubes is what they are, not dowels, they're tubes. So first of all, please watch this. You might have to play this part over and again, so make a note of the time and then rewatch this several times. You're going to take the cord and it's going to go through tubes 1, 2, and 3 and back through tube 1 from the beginning, and then come out. Once again, it's going to go through tubes 1, 2, 3, and back through 1 and then come out. And then you pull it tight. So tight that you want the joints, because you're going to create a triangle. And you want these joints, these corners, the vertices, to be nice and tight. Not so tight that it's causing any buckling of the mailing tubes. It's a pretty strong cardboard, but don't want them to actually mash the tubes, but you want nice tight joints. And once again, it goes through 1, 2, 3, and then 1, and then out. The next thing is they're going to grab 2 more tubes and feed the cord through the 2 tubes and out that one. I'm going to show you that again. Now, these were tubes 1, 2, and 3. This is tube 4 and 5. And the way this went was this was tube 1, 2, and 3. So here I'm going to do it slower. It's going to go through tube 4, and then 5, and then back through 3. I'll speed it up, it's a little too slow. Back through 3, and it comes out where you started feeding the cord in. So back where the little disc is, or the pencil, or whatever you have, and it's going to come out. Now you grab the last tube, tube number 6, and you feed this through tube number 6, and pull tight. When you pull tight, it tightens the structure till you get this shape. And once again, I'm going to just show you, I'm going to say the names of the tubes, numbers 1, 2, 3, 4, 5, and 6. I'm going to say them in the order they're threaded. It goes tube 1, 2, 3, 1, 4, 5, 3, 6. Okay? And now, you're going to take that cord and you're going to wrap it around through the joint here. You're going to wrap it around the cords that's there. So the cord comes up and then wraps around that. So you're making a loop through the joint. And once again, you pull tight. When you pull tight, it's going to create this structure. And at this point, the cord would be sticking out here. You're going to wrap it around and tighten and make a good knot, and then feed it back through tube 6. That was this tube. feed it this, that becomes this tube here. Feed it back through 6, that'll come out here. So watch carefully. It goes through 2. It goes 1, 2, 3. 1, 4, 5. 3, 6. Not. And then back through 6, and it comes out. And at this point, you're going to remove this disc or pencil or whatever it was stopping the cord from slipping through the whole thing. And you're going to tie this into a really good knot, making sure that all these joints are nice and tight. Okay, and not overly, this is a kind of a tricky one, not overly tight so that there's any crunching in these corners, but that they're not loose and wiggly, because the wigglier this is, our structure won't be sound. We need a total of 85 of these. Now that means that if 5 of us, 5 teachers were involved in this, it means each teacher would be responsible for 17 of these structures. And you could figure out which classes you want to do that. Do 2 or 3 in each one of your classes. Maybe you want to do 4 in some classes and none in one class. But if every class at least gets to make a few of these, they'll feel more a part of the whole structure. And that's part of this, is that we are creating a community of the entire math, all the math students, that there's going to be this big structure that they all had something to do with. If all 6 of us are involved with the creation of this, well, that means we only need to do 14, so definitely you only need to do 2 or 3 of these structures in any one class, which is kind of nice, because this will take some time, and you're going to have some and how many hands can you have on this? Once we get all those together, we're going to be taking 4 of them and just using zip ties. This part of it happens really fast. You just take these structures, and those zip ties, those are like cable ties and those plastic things, and you just zip, 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 just 6 of them, and it will make the second order. I don't know if we're going to need dowels for support. That will really depend on how tight these structures were made, whether or not that's going to, I'd really like us not to, because they will slide within there and it won't be a good thing. But if we need it, I'll have some dowels to help out. Once we have a bunch of these second order, we will take every 4 of these second order, and we will zip them together, and that's what the purple ones are. The next order, just again, 6 zip ties to make them. This is the structure we will probably have to make in the student center, because like I said, it's going to be about 9 feet tall. And then on the Monday at lunchtime, we will take 4 of those, and where these green ones are, we'll take just 6 zip ties. There's 6 of them here. Just take those 6 zip ties, and that's all it takes to put this whole structure together. Now remember, this is 9 feet up in the air, so we can't just climb up and do this, because this is made out of cardboard. It'd fall apart. The way we do it is we do these 3 zip ties here first. Everything's flat on the ground, and then we rotate these up and do this. There's definitely a method to it, and I can show you. It's kind of cool the way it happens, so it's fun to see. Please, I implore you, get some straws and some thread or string and practice. I did a few of these just yesterday to just practice the threading and understanding of it better, so that you'll know how to assist your students so that you can actually get this done, because we need to have all the tetrahedrons done on Thursday, all of them. And then Friday, we will, the first order tetrahedrons have to be done. The 85 of them have to be finished on Thursday. Friday, we'll be putting them together to make the other structures. And then Monday, at lunchtime, we will put the whole thing together. So this will not impact your class at all on that Monday, because that will be happening at lunchtime. And you'll still need to be doing a few things with your students on Thursday and Friday, because it might not take all the time, or you might have a few students who aren't involved in doing it. So this isn't necessarily, eliminating you from other things you need to do in your class. If you have any questions or comments, please email me. I appreciate you going through almost 20 minutes of this. Email me, look up Sierpinski triangle and Sierpinski tetrahedron online, so that you have some things of how you can make connections to your classes. I'm looking forward to this. I think this is going to make a really great start of the year for all of our students and for us as a staff as well, the math department, our team, to really feel like we're connected with one overarching idea, and I look forward to it. And I'll see you when school starts.